All right, today is the last lesson on elemental different geometry, and I want to briefly uh, show you how do we get the formula for the form obtained by the Gauss. Yeah, the idea is that the Gaussian curvature can be expressed in terms of EFG first. Okay, so what is Gaussian curvature? Origin definition, and how do we show that it can be expressed in terms of the first fundamental form and second fundamental form, right? So we begin with a surface patch sigma. Okay, it's defined on the okay. So using that, you have the first fundamental form, right? That's called the E, du square. And I use this notation, use the same du dv, and the G and dv square, right? The second fundamental form, okay? And those coefficients, are defined in the following form. And if you the first fundamental form is defined just as the inner product of those coefficients, right? E is going to be sigma u dot sigma u, right? F is sigma u dot sigma v, and the G is sigma v dot sigma v. Now, there was a Gaussian map, right? It's a normal vector. If you use a normal vector, then the second fundamental form, right, is defined by the following formula. L equals sigma u and n, right? M is a sigma uv n, and n is a sigma vv n. Okay, so n is a normal vector. Okay. Now then, okay, what we learned is we can express it. We can express this surface patch in the formula, in this formula, okay? Comma 1 and 2, 1 sigma v, and this h is n, okay? Because the dot product gives it, right? Sigma uv and the sigma vv. And using, okay, here's the point. Using the dot product, and actually gamma ijk can be expressed in terms of E, F, G, and their covariant derivatives, their derivatives. Okay, so the reason is just look at the first one, right? Look at the first one. You can use a dot product with U, okay? Then you get a form, right? And then you get gamma 1, 1, right? And the gamma 2, 1, sigma v, sigma u, okay? That's the first equation. Then gamma u dot sigma v. See? And as long as you can express this in terms of the partial derivative of EFG, then you solve the problem, because this is just a matrix. Okay, you get depends on how do you express the matrix, and this one you can express, sigma UVL. This part can be expressed as the left hand side can express in terms of the partial derivative of EFG. Okay, so we can, yeah, that's already given the formula here. So this is going to be half of u, right? And the uu dot EV, this is going to be FU minus half of EV, okay? So therefore, those coefficients can be expressed in terms of the EFG and the partial derivatives. All right. Similarly, you can do the work on the second equation, third equation. You can express everything. Gamma IJK, express them in terms of EFG and their partial derivative. That's one thing. The second one I want to talk about is the normal vector field. Okay, so the normal vector field, the normal vector field is a partial derivative, can be expressed in terms of, okay, it's a negative sign, in terms of A sigma u, B sigma v, because it's perpendicular to the normal vector, okay? And that will be C sigma u and the D sigma v, okay? Now what we can get here, this is going to be, so how do you determine those coefficients, right? So those coefficients can be, yeah, can be determined after you, actually, you can, yeah, you can get the matrix. The first one, the dot product was sigma u, and then was sigma v, and the same thing here, sigma u, sigma v. So you will get a matrix, something like that, L, M, M, N, okay? Yeah, so this is going to be E, F, F, G, and here A, B, C, D. So those coefficients can be expressed in terms of this this matrix A, B, C, D is going to be the inverse, right? L, M, M, N. Okay. Okay, those are the information we need, and the most important thing is the Gaussian curvature. The origin definition of Gaussian curvature you can express in using this formula. Now here it depends on the first fundamental form. Okay, it depends. It depends on E, F, G, and L, M, N. Okay, in this formula. Now Gaussian's main contribution, yeah. Gauss's main contribution is because of the work. Okay, his work. Okay. Oops. K can be expressed in terms of E, F, G, and their derivatives. Okay, now let's accept this fact. So that means if the surface is changing, okay, in the space, as long as the first fundamental form is not changed, then the curvature is not changing. That would be surprised. So imagine, okay, you have a family of sigma, yeah, let's say sigma, let's have a deformation. So I'm going to put a T here, okay? So you have a surface, it's a map, okay? So imagine that. So this will be ST, so it depends on T. When T changes, the surface changing the space, okay? But if, okay, the first fundamental form E du square, 2F du dv, and G dv square, if this one is independent of t, then what happened? Then the Gaussian curvature is independent of p, independent of t. Okay. Now, but this not if k cannot be expressed in terms of EFG and the partial derivatives, then you may imagine the Gauss curvature changes when the surface changes. You know, surface gradually, it's maybe depends on time t, maybe it's curved like that, you know, right? It's originally like this when t changes. Okay, so you have a family of a surface in the space. Think about when t changes. I think the second fundamental form would be changed. However, as long as the first fundamental form remains unchanged, then the Gauss curvature does not change. Maybe the mean curvature changes. Okay, here's a typical example. According to this argument. Okay, I have a what I'm going to do is here's a map, right? U and V. At the very beginning, I have a flat plane. Okay, so when t equals 0, it is a plane. Okay, so the map is, you know, it's easy to define. Okay, for example, t0 and u and v, it's going to be the plane. How can I define the plane? Okay, so this is just a plane in the space. Okay, there's yeah, u0 for example v, right? So that's a plane. Okay, and this is a plane in the y. It's a y, you know. Yeah. Maybe let me see. This is a plane starting from here. It's 1. Okay, and no restriction on u and v change. How about like that? Because this is a plane. Okay, passing through the x-axis, okay, perpendicular to the x-axis. All right, so that is a plane. Now you can gradually bend it, okay, to make a cylinder, right? If you make a cylinder, how can I describe a family of okay? So let me yeah. So this will be kind of a curved surface. Gradually you change. You can describe. I forgot how to. Yeah. So this will be. This always describes the cylinder. Okay, and you can find the formula here. It's a cylinder. Okay, with a larger radius. So the radius gradually become 1 when t approaches 1, for example. So you will see that you can check the first fundamental form remains unchanged. It will be independent of t. This procedure, okay, like a bend a piece of paper, okay, and it will be independent. Yeah, it will be independent the time t. Okay, EFG will be, so what you get here is EFG are independent of t. Okay, so the Gaussian curvature remains unchanged. Actually, it's going to be always there. The reason is k depends on EFG, but the EFG are all 0 in this case. Okay, they are all 0. Actually, you can make it. All right, so this is the idea. Just you bend a piece of paper gradually, okay, in the space to make a circular cylinder, okay. And this whole procedure, it's not necessarily circular, just bend it, just like any surface like that. You can make a curve, okay. Those are the lines perpendicular to that curve, like a fence, right? And then you can move around, okay. So it can go like that. Right? So this is a fence, right? And you can make it straight, you can make a curve. But then this, when you move around, you do not changes the fundamental, first fundamental form, okay? So that's why Gaussian curvature remain unchanged. Of course, that should be equal to Gaussian curvature of the flat plane, and which is going to be 0, okay? Which is going to be 0. All right. So now, how do we get some identities? Okay, Gauss was pretty genius. Okay, what we do is what we're going to do is I look at this identity, right? Sigma u, okay, partial derivative. Okay, remember this is a v equals sigma uv uuv, right? And sigma uv and the u. Okay, this is identity, one identity, and another identity is sigma v, and I think it's u. It's going to be sigma uvu and the sigma uu. Wait a minute. This will be the same. So I'm going to put the v here. So that will be vv, and that will be vv and the u. Okay, right? Yeah, sigma. Yeah. Okay, so those are the two identities come from the partial derivatives, right? The first identity, let's see, how can we solve the problem, okay? And I'm going to expand it, okay? So I will remember this gamma u, sigma uu is expressed in terms of this, right? So I just give you the idea how to get it, right? This is going to be sigma 1, 1, sigma u, right? Sigma 2, 1, 1, sigma v, and ln, the partial derivative, right? So let's see what we got here. So sigma 1, 1, 1, okay? And the sigma 1, 1, sigma uu, okay? So sigma uv is going to be, okay? You know, this is sigma and uv, right? Sigma uv, I'm going to still put the sigma uv here because I don't want to directly substitute. Yeah, sigma uv, okay, that's two terms. And the gamma 211 and the this is a v, okay, don't confuse. Sigma v. Okay, then have a two terms, LV n, okay, and LNV, and plus, okay, plus, yeah, so how many terms are we going to get? You're going to get total 6 terms. Okay, I just show you one example. Okay, so this is identity, and then you can replace this one by another. Yeah, this can be replaced by above formula. Okay, so this will be let me put this one here. This will be, use a red pen. This will be sigma 121 sigma u, sigma 122 2 sigma v, and the m. Okay, and this will be replaced by sigma 221 u, sigma 222 sigma v, and lmn, right? Okay, then you know, this is a sigma uv, sigma uv and the v, right? Sigma uu and the v, and then you use this one, the one on the right hand side. I just show you, we did this, right? So this is the here. Okay. Yeah, this is the sigma u, right? Then you do the same thing. If you are told that you can eventually express K in terms of EFG by N, that partial derivative, probably can work out by yourself, okay? So the second one is gamma 1, 1, 2 sigma U, gamma 2, 1, 2 sigma V, and M, N, and the partial derivative, right? So this is nothing but sigma UV and U, okay? And then they're equal, you know, they're equal. These two are equal, right? These two are equal. So then similarly, you can compute gamma 1, 1 and U, sigma U, and the gamma 1, 1 and the sigma, sigma UU, right? Yeah, sigma U. Okay, sigma UU will be sigma 1, 1 U and sigma 2, 1, 1, sigma V and L and N. Okay, and then the second one, and this will be sigma VUV, right? Yeah, careful, it's about, okay, and the last one. And I have to say that this can be also changed. So let me replace this one by, right? We already have we have the expression, we have the so-called A, right? Negative A. Let me give you the, yeah. Yeah. And V will be C sigma U and D sigma V. Okay. And this one, remember, it's going to be replaced by negative A sigma U, negative B sigma V. Okay. So those two are equal. Then you can just compare the coefficients, and you get lots of identity from that. Okay, you got lots of identity that, and the first identity you probably don't need it. It's going to be LV. Look at, right? LV compares this N, right? LV minus MU. Okay, and you compare their coefficients. This can be L. Yeah, we have N here, right? So you can, but we don't need that actually in the computation to express the Gaussian curvature in terms of EFG and their partial derivatives. You know, yeah. But this is what you can get. And for the other one, you only get one equations here when you compare the coefficients. This comes from the coefficients of N. Then you compare sigma U and the sigma V grouped together because these two are identical. So finally, you will get several identities, and if you use one of the identity, compare the coefficients sigma U, you know, yeah, sigma V, and this N, right? It's going to be 0. So this part gives you this one. Then you can also look at those two, okay? And then the coefficients of those two, it's going to be gamma 1, 1, I think of V, gamma 1, 2, U, and this is gamma 2, 1, 2, gamma 1, 2, gamma 2, 1, 1, gamma 1, 2, 2. Okay, and then plus CL plus minus AM. Okay, so look at this identity. We're almost there. The reason is, I just want to give you one expression, okay? And you can use this one, the second one, get another identity. Okay, so total you're going to get 4 identities. Why? Why you get 4 identities? So let's get for 1 identity, right? And this part, C and D is here. C and D is here. C and D is here. Given by this formula. Okay, so you will, using this identity, yeah, finally, you can, yeah, let me move, yeah, let me mention this identity here, okay? So I'm going to call it a star, okay? That's a star, okay? By star, CL minus AM is going to be negative FK. Okay, K is it's actually is negative F L M L N minus M square EF minus EG minus F square. Okay, so that's a K. Okay, so you get 1 identity. Okay, you actually will get 4 expressions. It's surprising. You get 4 expressions for K. And use this part, you get another expression. Okay, then using the equation, you see they all come from here. They all come from here. So this equation gives you 2 expressions for E. Okay, 2 expressions for E. First of all, you expand it, then you compare those 2 are equal, right? Those 2 are equal, and you compare the coefficients. You get the 2 identity. One's from here, one's from here. That must be 0. The one from here, I just give you an example, and you can get because of this identity, you can get an expression for K, okay, which I express in terms of. So we get an expression for K, and that is an interesting identity. Yeah, I think we got the 1 identity, which is going to be, yeah, so we get the identity, following identity, F. I just need the 1 identity, okay? F is going to be, yeah, F is going to be gamma 1, 2, U, and the gamma 1, 1, V, plus gamma 2, 1, 2, gamma 1, 2, gamma 2, 1, 1, gamma 1, 2, 2. Okay, that's all we need, okay? So this is, and similarly, you can get the rest of them. That's all we need here. Now, clearly, gamma, yeah, we know that gamma ijk, okay, can be expressed in terms of EFG and their derivative, right? Okay, so this implies K can be expressed in terms of, although it's complicated, EFG and their derivatives. Okay. So there are other 4 identities that give us similar equations. Okay, so they're not, and later on, okay, one can summarize, simplify. Finally, in the book, there was a given formula. In fact, okay, this is a pretty technical computation. In fact, some guy can organize all the coefficients, express them directly in terms of EFG. It's very complicated, but then they make it in certain form, so it's easy to compute. Okay, and the FV minus half of GU and half of GV, and here half of EU and EF FG, and surprise, this is three. It's a 3 by 3 matrix. Okay, so I think if we express in this form, maybe it's easy to memorize. You know, where we needed to organize them in better way. It's a really magic. I think this is obtained by Gauss. Yeah, we really admire him for such computation, you know, a couple hundred years ago. Okay. So this is you see, and it involves a second order derivatives of the coefficients EFG. Okay, although this is just equal to L n minus m squared EG minus f squared. You know, you can say that, well, this form is much simpler, but you needed to know as the relative positions of the surface in the space. But the first formula is independent of the relative position of the surface in the ambient space, in three-dimensional space. Okay, I already explained to you that when you have this kind of a surface, right? You know, if you move moving it, you know, a family of, you know, if when time changes, if the surface in the space changes, as long as the first fundamental form remains unchanged, then the corresponding curvature will never be changed. Gaussian curvature never be changed. This is a really surprise to me. Okay, and it's a pretty important discovery. Okay, so if we have a family of a surface in the space, okay, this family, you know, described by this family of a surface patch, and when t changes, the surface changes in space. But as long as it does not change intrinsically, means the first fundamental form is independent time t. Okay, the coefficients. Then the Gaussian curvature at the corresponding point remains unchanged. Okay, if it's 0, then it's always 0. Okay, this particular case, this is a line. This surface consists of lines perpendicular to the given curve, and the curvature is always equal to 0. Gaussian curvature, but the mean curvature is none. Okay, the reason is you can make it, you know, you can change it gradually, and it become a straight flat plane, and then yeah, since the Gaussian curvature has not been changed, it remain unchanged, so the flat plane, the Gaussian curvature is 0. That's why this surface has 0 curvature. Okay. Yeah, there are some special case. Okay, I have to mention it. In case if f is 0, that means they're perpendicular. Okay, two curves, sigma u and the sigma v. This is a 90 degree always. Okay, so in that case, the curvature can be this formula can be simplified. Okay. Right. So that above formula can be simplified to this form. And we can also further move if f is 0 and e equals 1, you can even make it much simpler. Okay. So you will see that e is 1, so second term here is going to be 0. So Gaussian curvature is just equal to here's g, and that's a gu and the square of u. Okay. Okay, and then you can rewrite it in the form. Okay, that's great. That's great. Okay, so using this formula, you can compute the surface Gaussian curvature surface erosion quickly. Okay, so we have an example. I'm going to finish this example. The surface of a revolution. Okay, the surface, and here f is positive, f prime u square, and g prime u square is going to be 1. Okay, then E is going to be, you don't need to calculate the LMN, right? The second fundamental form. So Gaussian curvature is pretty simple right now because G is going to be f of u. So by the above formula, you see, here's the f of u and the partial derivative, right? And here, that's it. And if you want to make it positive, you just need to differentiate twice. Yeah, differentiate twice. Okay, the function. And then, if, to find if we assume that, okay, assume that k is constant, then the above equation becomes an ODE equation. So as long as you can solve it, then you get a constant curvature, get a surface erosion with constant Gaussian curvature, right? Yeah. All right. And there's a general solution for this. There's a general solution for this. Okay. It is going to be depends on sign. Depends on sign. Okay. So if we can we can write down the general solution for this equation. Okay. When k is positive, you get sine function. When k is negative, you get a hyperbolic sine function, hyperbolic cosine function. Okay. So the let me see, sk defined to be, okay, this will be when k is positive, I'm going to use a sine square of k and u. I'm going to choose here. Yeah, when it's a 0, I let it be u. When k is negative, and there'll be square of negative k, hyperbolic sine negative ku. Okay, and the cku, just assume that sk prime u. Okay, the partial derivative as just the derivative. This actually becomes cosine square of u if u is if k is positive, and that's going to be 1 if k is 0, right? And hyperbolic cosine u if k is negative. Then the general solution to the above equation, depends on the two coefficients. Each of them has a solutions, okay? So f of u equals a sku b cku, okay? So this is a s means sine, k, c means cosine. All right, so this AB are constants, where AB are constants. So those are how do we get the general solution? Right, then you get a bunch of surface of revolution with constant curvature. Right? Okay, this explain to you. This explain. Let's take a look at the Earth. Okay, and okay, so I'm going to consider map. Consider map from surface 1 to surface 2. This is isometry. Okay, this is we assume that's isometry. Okay. Okay, you call that right? Consider in isometry. Isometry means it preserves the length of the curves. Okay. Preserving the length of curves. Okay. Isometry, yes, length of the curves. So that means it's a diffeomorphism, preserve the length of curves. This implies if this is a surface, that's another surface. Maybe the other one is a flat, you know. So I don't need to draw the similar one. I just draw. Yeah, I draw it. Looks like that. S1, S2. Right. So that means if sigma is a surface patch, then you can consider sigma tilde. This is another surface patch. So that indicates, okay, the first they have the same first fundamental form with respect to the surface patches. Okay. This is S2. The first fundamental form defined by sigma f e du square 2f e du dv and the g dv square, because f is isometry. So with respect to that surface patch, you also have the same exact formula. Okay. Because f is isometry. Okay. F is isometry. Okay. So that means they have the same. Okay. Yeah. So S1 has the same Gauss curvature at P as S2 at F of P. Okay, so there's a corresponding point that Gaussian curvature is the same. So that means you cannot make the surface of the sphere flat. Okay, you cannot make the surface flat isometry. Okay, so that concludes that. Conclusion is there's no local isometry, okay, which maps a region S on the sphere with radius r onto a region R2. The reason is the curvature R2 is 0, the curvature S2 is 1 over R squared. So there was this is a sphere, right? and here have a region, and here's R2. So you cannot find an isometry. So isometry means it preserves the length of the curves on the sphere, and you cannot find it. The reason is if it's isometry, and then you get the same first fundamental form with respect to those surface patches, special surface patches, and the curvature, Gauss curvature should be the same at the corresponding point. But Gauss curvature on the R2 is always 0. Gauss curvature on S2 is always positive. Okay, that's why there's no such isometry. So when you draw the map, okay, world map for the Earth, if you want to draw the map on the piece of paper, you cannot do that without changing the size of without to stretch the country, like Alaska, Canada, those regions in the north side, Russia. So when you look at the world map, Russia always looks much larger than the actual size, just because they're close to the North Pole. Okay, so see, geometry is very useful. When you work on some projects related to space science, anything. So okay, and mechanical engineering definitely require geometry, and there's lots of area that requires a geometry. Okay. Right, okay, let me check if anything else I needed to talk about. This is section 10.2. I think that's all I want to talk about. Okay.